Previous lessons, we looked at some tables, some exponential tables, and we're able to see a proportional growth pattern from looking at the initial table. Today, we're going to look at some where you don't see that proportional growth pattern looking at it straight from where it is. And that's because there's a vertical translation on the function. So if we can add or subtract a constant from the output values, the y values, to reveal a proportional growth pattern, then the initial function was also exponential. It just had that vertical translation. So we've got some table values right here. And it says selected values for several exponential functions are given in the tables below. For each, find the constant value that can be added or subtracted to the output values to reveal a proportional growth pattern. So we're going to look at what can we add or subtract to this number that will create a proportional growth pattern. So some of these are going to be a little bit easier to see than others. Like we look at this first one here. And so if this was 6 and this was 12, 24, 48, and 96, then we can see that this multiplied by 2 times 2 times 2 times 2. So you see that proportional relationship there. So that is one option in looking at it. Our R value here would be 2 because that's what's being multiplied each time, or the B value. And so we can say f of x here. My first value is 6, but it's actually 7 right here. So we know that we need to add 1 to whatever this value is. So our initial value should be 6. We said that rate is 2, and we need to add 1 to get this next value. Each one of those was added by 1. So this one was a little bit easier to see that. In some cases, it's not going to be as easy to see it. So looking at this second table, it's not quite as easy to see it. So we're going to have to dig a little bit deeper on this one in order to do it. So on this one, if I looked at these values here, I can see that if I add 2 to this, it would give me 4. If I add 2 to this, that would be 12. Add 2 to this is 36, 108, and 324. So we've added 2 to each one of these, giving me that vertical translation of 2. But now I can see there's a common ratio right here. It is being multiplied by 3. So 4 times 3 gives me 12. 12 times 3 gives me 36. Times 3 gives me 108. And so our R value here is 3. And so in this case, my g of x would be equal to 4 is that initial value right there that I have. And so that's my initial. My multiplier, or common ratio, is 3. And we said we added 2 to each one of these to get those new values. And so I need to subtract 2 to get me that value right there. Of course, you would want to check the value. So I'm going to plug in 0 here. And so that would give me 1. 4 times 1 is 4. Minus 2 gives me that 2 right there. If I tried 1 right here, that would give me 4 times 3, which is 12, minus 2, which gives me 10. So that's one of your options for looking at these values to find that vertical translation. I do want to show you some other options just in case you can't recognize that vertical translation that's being added or subtracted. So you could find your differences here on the table like we have in the past. And so this went down by negative 32. This went down by negative 16, negative 8, and negative 4. So I found my difference in my y's here, and I have equal lengths on my x. That's why I can do that. So I found my differences, and then you're able to see that common ratio better. We had a negative 32 here and it went to negative 16. So I had to multiply times 1/2. And then if I multiply times 1/2 and I multiply times 1/2, so my ratio there would be the 1/2. Now, if I think about the value here is at negative 32, so this right above that should be 64. And so that would be my initial amount would be 64 times the 1/2. Now, again, I test this. If I put this in 0, that would make this 64, but it's actually 63 there. So that would be 1 less. And so we've got that. So in order to get this common multiplier, you can get your common differences there to do that. One last step on showing you that. So we said this one was a little bit harder to look at. These, you could see the pattern just a little bit faster because this was only +1 and -1, and it happened to show you those numbers a little bit faster. If you can see the pattern like you can here, that's great. That's faster, and so you want to do that. But I want to show you, if you can't do that, how to get that table anyways. So we have our values here, and we said we can find that common multiplier by finding the difference. So I would do that first. And so I find my difference there, and that's 8, and that's 24. And then we've got a difference of 48 here. Sorry, that's not 48, that's 72. And then we've got a difference of 216. And so there's my differences. Oh, you can't see that. Sorry about that. All right, so there's my differences on the table. And so all I've done is rewrite this table right here just so that we can talk a little bit further about it. So I found my differences here, and then by looking at these values, I can see that this was multiplied times 3, multiplied times 3, multiplied times 3. So I have my ratio as 3, which is the same thing that we had seen right here. Okay, so either way, you're going to get the same exact thing. Now, if I have no other options on how to figure this out, but I've got this value, well, I've got a bunch of points right here. So we can set up a system of values and do y equals a times 3 is my b value, x, plus that d value, that vertical translation there. And then I can use any of the 2 points. And so I plug in 2 for my y value and 0 for my x value. And so this is just 2 equals a plus d, because anything to the 0 power is 1. And then I do the same thing for a second point. And so I get 10 equals a times 3 to the first power plus d. 3 to the first power is 3, so that's 3a plus d right now. And if you remember systems of equations, we've got 2 variables here, so I can set up my system, and I do 2 equals a plus d, and then 10 equals 3a plus d. And I'm going to go ahead and subtract these. And so that gives me -8 is equal to -2a. D minus d is 0. And so a is equal to 4. And so there is my initial value. So I've got 4 times 3 to the x power. And so then to find the d value, I have 2 options. Again, I can plug in the 0 there and then make it equal to 2. Or I can go ahead and plug this into the initial equation here. And so we get 2 is equal to 4 plus d. I subtract the 4 and I get -2 is equal to d. And so there's my equation of y equals 4 times 3 to the x minus d. So you do have a couple of different options here. Again, we tried to find that vertical translation first in order to get these values. And then we create the equation using that pattern. So if you can see the pattern, that's the easiest way to do it, but you can create a system of equations if you can't figure that out. All right, so to write those exponential functions, we need a common ratio and we need the initial value. And so if you've got both of those, that's the easiest way to write. If you don't, again, if you've got 2 input or output values, then you're also able to find the equation that way. So we're going to look at a second one here. It says for 0 to 30 minutes, the number of fans inside a large sports stadium can be modeled by the exponential function right here, where f represents the number of fans inside the stadium 2 minutes after the doors open. There are 47 people in the stadium 2 minutes after the doors open, and there are 602 fans inside the stadium 20 minutes after the doors open. Use the given data to write 2 equations that can be used to find the values for constants a and b in the expression for f of t. And so in order to do that, it gave us 2 different points. It says 47 people in 2 minutes. And so I'm going to write that as one of my points. And then the other one is the 20 minutes at 26:02. That's how many people were in there. So to write this equation, again, we're using this part right here, f of t equals a times b to the t power. And so here is my t, and here is my f of t. So I can write 47 is equal to, I don't know the a value, I don't know the b value, but the t is 2. So there's one of my equations. And then for the second one, I can write the 26:02 is equal to a times b to the 20th power. So there are the two sets of equation that we can write in order to write to find that a and b value if we needed to. Once you've got those points, though, the easiest way to do that is to do it on your calculator. So we've done that before where we're doing the regression. And so we'll model that again, just to remind you. In this particular case, there's my 2 points right here. And once I've got 2 points, I can go to stat, and I can put in the 2 points that I'm given, making sure I match that t value with the f of t. And then I hit stat, calc, and I want to go to exponential regression, which is the 0 right there. X is the L1 and Y is the L2. That's correct. That's what I put it in. For store regression equation, we hit alpha trace to get the Y1. And then we hit, oops. And then we hit calculate, and there is our equation. Again, we want to make sure we keep 3 decimals. And so that equation, when written, would be y equals 30.089 times 1.250 to the t power. And remember, you want to keep that 0 there because you want to show that it was a rounded number to keep those 3 decimals. So do not put 0.25. You want to have that 0 there to show that that was a rounded value. So here we're looking at the same concept, except it's got a table of values instead of writing the information out in context. But the process is still the same. They have given us 2 points here. And so it says use the given data to write 2 equations. And so we would write the 21.54 is equal to a times b to the 3rd power. And then our other one would be 3.62 is equal to a times b to the 8th power. So those would be the 2 equations. To find a and b, you've got a system of equations there, so you can do it as a system of equations, or you can go into your calculator, which is the easiest way. We're going to hit stat, and then we're going to put in our information. So 3 and 8, 21.54 and 3.62, making sure we match those. And we go down to our exponential regression alpha trace, y1, and we calculate. And so there is our equation. And so we would say A is equal to 62.801, and B is equal to 0.700, since this was 0.999 there. If you wanted to write the equation, we would say g of x is equal to 62.801 times 0.700 to the x power. All right, so a quick reminder from Algebra 2. E is the natural number that we use in Algebra 2. It's just like pi, but for Algebra 2, this is the number you should know. E is equal to 2.71828, and it continues. That number is found on your calculator. So to the left of the 4 right there, you see e to the x power. So anytime you hit second and then the natural log button, you are going to get that e value right there. And so if we put it to the first power, there is our e. In many of the exponential cases, they'll be using the e value, and you do want to use the one on the calculator with the entire thing instead of rounding. Does the number of bacteria be in a particular culture can be modeled by the exponential function right here, where t is measured in hours. Let a of t equal a times b to the t power. be an equivalent expression for b of t. Find the value of b. And so b is the one that's being raised to the x or t power to the variable. And so when we look at this equation, what's being raised to the powers is e to the 0.31. So to find the b value, we would hit second and that natural log, and then we're going to raise it to the 0.31 power. And so there would be, there's a glare there. So that would be my b value, 1.363. All right. We always want to keep going back to that average rate of change because that's a big part of our pre-cal. So right here where it says find the average rate of change of b of t over the interval from 1 to 7 hours, then our average rate of change would be a of 7 minus a of 1 over 7 minus 1. Remember, that's the difference in your y's over the difference in your x's, basically. So we would take our 7 and plug it into the equation right there so that we can find a of 7, and then we would do the same thing for 1. And so we get 148.89 minus 23.178 over 6. And so I am going to put this in the calculator just so that you can see. You do want to use the entire thing. And so 17 e to the 0.31 times 7 power. And then same thing, 1. And so you do want to use these longer parts of your equation. So when I do this, I'm going to go alpha y equals to get numerator over denominator. And then I'm doing, you can use the arrow key to highlight that. So I highlight that and then minus over 7 minus 1. So do use that entire number. Don't round until the very end because that can change your answer quite a bit. So 20.952 would be our average rate of change. All right, it says find the number of bacteria B predicted by the model after 15 hours. And so for that, we would plug in the 15 into our T. And again, we do not want to round, so you want to put this into the calculator exactly the way you see it. And so we get approximately, and I'm going to say 1778 bacteria. I did go to a whole number because bacteria, we're not going to have a decimal value of that. All right, for example 5, it says, after 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by the exponential function d of t equals a times b to the t power, where t represents the number of years since deer were first introduced to the wooded area. The population of deer increases by 13% each year. Find the values of a and b and use these values to write the expression for d of t. All right, so when we're talking about this here, d of t is going to be my population of the deer. And it says that we introduce 50, so that's going to be our initial amount. Remember, the initial amount is always the one that goes in the front. And so then we are going to multiply that times our growth factor. And so it is growing by 13% a year, but you are going to keep that initial 100%. And so the 100% would be the 1 plus the 13%, and we move the decimal over 2 places. So 100% we move over 2 places is 1, and 13% we move over 2 places, and that's 0.13 to the t power. So that would be our equation there. According to this model found in part A, what is the population of deer in the large wooded area after 6 years? Well, then d of 6 is equal to 50. I'm going to go ahead and simplify that to be 1.13 to the 6th power. And so that's going to give us approximately 104.098. But it's deer again, so we would want to use a whole number for that. And so 104 deer is what we're looking for. All right, find an equivalent expression for d of t where t is measured in months instead of years. And so we would say d of t is equal to 50 is my initial. still growing at 13%. So we'd have our growth factor as 1.13. Now, up here is where it's going to change. We said for each year it would be t. Well, there's 12 months in a year, so this would be t divided by 12. Because now when we put 1 month, it's only going to do 1/12 of the year. And so then 2 months, 3 months until we have all 12 months accounted for. So one of the questions that's not on there, but I do want to talk about a little bit here is going the other way. So if they gave us this equation, or we wrote this equation, and we're asked to find when is there going to be a certain amount of deer. So at that point, you don't have a value to plug into the x here. So when we were asked about 6 years, all I had to do was put the 6 in the exponent and find it. But what if we were asked when there would be 150 deer? Well, since we haven't solved those yet, but I do want to start working towards that, you can solve using the calculator by plugging that into your y1 and then the 150 into y2. Now I would have to open my window because remember the standard window is just -10 to 10. Sorry about that. All right, so that's our standard window, -10 to 10, but I just asked it to find me 150 for the y, so I know this has to be bigger. Now exponentials grow pretty quickly, and so you don't have to open the x very much, but you should open it a little bit just to see what's happening. So there's my exponential, and then there is the 150 deer, and so the point where they intersect would be my solution. So I can hit second trace intersect, enter, 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 and there it is at 8.989. So 8.98 years would be the answer to that. That's when there would be 150 deer. So that's just a quick look at what's coming up, just making sure that you can work the other way as well. All right, to wrap up what we were just talking about there on writing the equation, anytime that you have that percent increase, we're going to start with the initial amount of A, and then we have that 1 plus our rate there, our percentage. And you're going to remember to move it over, the decimal over 2 places to get that. If it's some kind of percent decrease, then it is our initial amount, and it's going to be 1 minus R. Now, it's not always going to say decrease or decay, so you or growth. So you need to look at those words in the context to figure out if it is going up or going down. So looking at things like depreciation and what's happening in the actual scenario. So here's some examples of that. A home's value, V, is 200,000 and increases by 1.5% per year. So there's that word increases. So I know I'm going to have the plus there. My growth factor is going to have to be greater than 1 for it to increase. So for my home's value here, we'll call that H of T. I would start with 200,000. That's my initial amount. And then it is 1 plus 0.015. Remember, you are moving that decimal over 2 places. All right, for Mr. Breast's yard is getting overrun with weeds. The first year he bought his home, there was 1,800 square feet of grass. It is decreasing by 28.1% per year. There's my word decreasing, so I know I need it to be less than 100% for it to go down each time. And so here we're going to say our grass, so G of T, is equal to the 1,800 it started with, and then 1 minus 0.281 T. And so notice that when you simplify this, that's going to be 1 That's going to be 1.015 as the growth factor. And then when we simplify this second one, we get the 1,800 times 0.719. And when we talked about growth and decay as an exponential, we said that when it was bigger than 1, it was a growth. And when it was between 0 and 1, it was a decay. So you see that right here. This is the decay once we get that 1 minus on there. All right, a population P of fruit flies is currently at 150 flies, but is increasing by 205% every day. And so we can write our equation. We started with 150. Now this would be 1 plus 2.05 as we move that decimal over 2 places. And so this would be 3.05 on our equation. Another one that I want to refresh your mind from Algebra 2 is that half-life and double time. And so for half-life, again, our initial amount always goes at the beginning, but our factor here would be 1/2. And then for double time, again, we would start with the A value for our initial amount, and that factor there would be a 2 for double. Okay, so for an example here, there's 150 grams G of radioactive material. Its half-life is 4,400 years. So write an equation for this one. And so we would say G of T is equal to 150 grams, which is our starting point. And then that's going to be 1/2 because it's a half-life. Now I can't just put a T here because then every year I put in there, it's going to take half. And we don't want that. We want it to take half in 4,400 years. And so we would divide this by 4,400. Make sure you're digging into what that context is happening and knowing that T stands for years. So every time you put a year in there, it's going to do that half. So it's really important that you notice what that part of it is there. All right. And then for our example 11 here, Mr. Bean's parents currently have 95 descendants. The number of their descendants is doubling every 15 years. So we started with 95. It is doubling. And again, it doesn't double every year. It doubles every 15 years. So we would divide that by 15 right there. So there's some modeling of the different exponentials that you're looking at from tables, from context. Just get comfortable with the data that it gives us.